Hello there and welcome back. This is our video on derivative graphs. What does the graph of a derivative look like and how does that compare with the graph of our original function? And we're going to see a lot of interesting connections in this video as we go forward. We're going to keep the actual example part of the video pretty short. I've got two examples on this one because we got a lot of terms to introduce and talk about. So let's get going. Just take a moment to think and to appreciate the graph of this cubic function right here. All right, so we got a cubic function off here to the right. And this cubic function in particular has a relative maximum at x is equal to -2 and a relative minimum at x is equal to 2. In between, all right, this graph increases all the way up till x equals -2, decreases all the way down to x is equal to 2, and then increases from x equals 2 beyond. All right, and you probably knew a lot of that already because you took pre-calculus. You talked about increasing and decreasing portions of functions. But we're going to add a couple more terms to all this. In particular, you'll notice that the shape of this graph looks a little bit different to the left of 0 and to the right of 0, if you notice. As you start to see this, it becomes more and more obvious, but it's like we put two puzzle pieces together. And what's happened is we've got this function where the graph starts out with a really steep slope, all right, all the way up, and the graph gets less and less steep with its slope all the way until we get to -2. So we started out with a really steep positive slope, and then it levels off until we get to -2. And then we have negative slope that's getting steeper and steeper for a while, and then it starts to level off right here around x is equal to 2. And then we start to have positive slope that gets steeper and steeper. Well, what we have are two pictures here that could get put together at x is equal to 0. We're going to give that phenomenon a name. We're going to say that means concave up and concave down. So if you see here in yellow and in green, I have two different types of shapes here. So let's start with the green. In green, we have what's called a concave up function. One way of looking at it, does it look like it's up like a cup? In other words, if we were to pour water into this portion of the function, would it hold water or will it spill it? And over here from 0 to infinity, we would notice that we would hold water. So we call that concave up. In yellow, we've got this function that is what we call concave down, or down like a frown. So you got to imagine that this portion right here of the graph is some sort of a frown of a person, right? So it's oriented, so it's a down like a frown. Also, if we were to extend this analogy of holding or spilling water, it would look like we've taken a cup and we've turned it over, and all the water goes spilling out the bottom. All right, so concave down all the way up until 0, concave up from 0 to infinity. This point 0, 0, we're going to give a special name. We're going to call it a point of inflection. Right, so that's where our concavity changes, where we went from being concave down to concave up. So that's called a point of inflection. And don't worry, we'll go through all the examples in just a second, all the definitions I mean. Let's compare. We've got our function graph right here. And if we were to kind of compose an idea of what the slope looks like at every point, what kind of graph would we get? Well, like I said before, when we start out and going all the way up until x is equal to -2, we have positive slope. But the slope is really, the function's really steep here at the very start, and then it starts to level off. So that's reflected in our graph of our slope by saying, well, the slope is really high with its y values to start, and then as we get closer to -2, we get slope that's closer to 0. When we pass -2, we start with our negative slope. So you see down here, we're going to have negative slope right here. Negative slope, which starts out close to 0, and then we're going to get steeper and steeper negatively. So we have more and more of a negative slope until x is equal to 0, and we have a slope that's the highest negative value. We say that's a slope of -12. And then as we get past x is equal to 0, our slope is still negative, but not as much until we get to x is equal to 2, when our slope is 0 again. And then past x is equal to 2, we see that we have positive slope again that's getting steeper and steeper. So we're going to have a higher and higher y value for our slope graph. Well, how do the points correspond? we had a relative maximum at x is equal to -2. All right, so on our graph, we went from a positive slope to a negative slope. Well, what do we see in the graph of a derivative? We go from positive to negative. At x is equal to 2, our graph of f had a relative minimum. So our slope went from a negative slope and turned around to be a positive slope. So our slope graph is going to have negative slope into positive slope. And finally, we have a point of inflection at x is equal to 0. And what's happened at x is equal to 0 is we've gone from concave down to concave up. We've gone from the steepest negative slope we possibly can get to starting to become more positive with our slope. And so the graph of our derivative will show that we've got a relative minimum. It's the lowest possible slope we could have. Okay, in a little bit, we'll see that we could have a relative maximum also on the graph of f prime if there is a point of inflection on the original graph. Finally, we saw before that this graph was concave down all the way up until x is equal to 0 and concave up afterwards. Well, what's the slope graph look like? All the way up until 0, the slope decreases, it goes down. Right, we can see that in the fact that we're having more and more negative slope all the way until we get to 0. And then past 0, our function is concave up. So our graph of our derivative will be increasing because our slope is continuing to go up. So there's lots of comparisons between the graph of a function and its derivative. So let's define a few terms really quick. We're going to say a function's increasing if f prime is bigger than 0 for all values in an interval. Decreasing if f prime is less than 0 for all values in an interval. We'll say a function has a local maximum or a relative maximum if the slope f prime changes from positive to negative. So positive slope to negative slope. And a local minimum if our slope changes from negative to positive. Right? We see that we went from a negative slope, decreasing, to increasing. Some new terms for you. And these new terms are concave up. We say if f prime is increasing, so this right side of the graph is concave up because our slope went from large negative to 0 to 2 to 3 to bigger slopes here on the right. All right, so the slope goes up means we're concave up. If the slope is going down, we are concave down. So this portion right here has our slope going down. So we went from a slope that's a large positive number to a smaller positive number to 0 to a negative number. So the slope's going down on the number line, going from a positive number to a negative number. Finally, we have a point of inflection. If f prime goes from increasing to decreasing, or f prime goes from decreasing to increasing, right? So right here at 0, we had a point of inflection because the slope went from a large negative number to less of a large negative number. So there was a change in concavity right here. Here's all that in chart form. You might find this helpful. So pause the video and go through. This is just a way for you to organize all the things that happen with the function and what happens to the derivative. Okay, so this is a summary of all that. So pause the video and we can get all this down in chart form. Another thing that's important is that we've got 4 different types of function graph sections. So a way of looking at that is on the left, we've got our 2 situations where we have a concave up function. Concave up and decreasing would be right here. Increasing concave up would be a little portion like this. On the right, we've got our 2 situations where we're concave down. We could either be increasing and concave down like a frown, or decreasing and concave down like a frown. Right? So these would be helpful to have down in your notes as well. I didn't put a specific section in there, right? But these 4 sections will come in handy as we start to graph our functions. All right, so our first example from the graph of f below, we want to sketch the graph of f prime. So this is the graph of a function. What does the derivative look like? So it's important to find major features when you're doing this. For example, where does the graph increase? And this graph increased from -2 all the way up till -1.253, and from 0 to 1.253, right? So in our derivative graph, what we're going to see is that f prime is bigger than 0, right? We have positive slope in those regions. Another thing you might look at is things like where are the relative maximums of the function. Well, there's a relative maximum of the function at x equals negative 1.253 and a positive 1.253. So the graph of the derivative will go from positive to negative. That would make sense because the graph goes from increasing to decreasing at that point. So the derivative will go from positive to negative. Relative minimum at x is equal to 0, so the graph of the derivative will go from negative to positive. So remember, the graph of the derivative is different from the graph of the function. Finally, we're concave up from somewhere about negative 0.8 right in here to positive 0.8. And you can see right here we went from concave down like a frown. You can imagine that you're dropping water here. And then we've got concave up here. This area would be holding water. And then concave down, the water's falling out. So how do they compare? Oops. As we can see, when the function had a relative maximum, the derivative went from positive to negative. And when the function had a relative minimum, the derivative went from negative to positive. Same right here at 1.253, derivative went from positive to negative. And you can see everywhere we were increasing was right in here and right in here because the derivative or the slope is positive in that region. So this region corresponds to where the function increased. All right, last example here, given the graph of a derivative below, give an approximate sketch of the graph of f. So this is the other way around. This is what the slope graph looks like. Can we reconstruct what the function looks like? Again, let's try to name some key features. So f prime is positive from negative 3 to 3. So that'll be a situation where f will increase. F prime is negative everywhere else, so f will decrease in all those spots. F prime changes from negative to positive at negative 3, so f will have a relative minimum. X is equal to negative 3 and a relative maximum because the derivative changes from positive to negative at x is equal to positive 3. Derivative increases all the way up till 0, so f will be concave up, and decreases from 0 to infinity, so f will be concave down there. I think it's helpful when you do this to actually draw the graph using those 4 pieces I mentioned. One more thing, f prime has a peak at x is equal to 0, so we say f has a point of inflection there. So I decided to put all this together, all these key features. So let's scroll through all those here. From negative infinity to negative 3, you'll notice that in that case we had the derivative be negative, so f would be decreasing, but it's an increasing derivative, so the function will be concave up. So that little piece will look like this. From negative 3 to 0, the derivative is positive, so f increases, and the derivative is increasing, so the function was concave up. So we have another little piece right there. Beyond 0 and on to 3, we have the function increasing and concave down, right? Because the derivative was positive but decreasing, so we get this little section right here. And then the derivative is negative past 3, so the function decreases and is concave down because the derivative decreases. So as I'm putting this together, right, I'm noticing where my intervals were, where I decrease at all my important points there, and my concavity. So I get a nice little picture of what the graph looks like. And when you put it all together, right, you'll see in blue, I've got my lovely little picture here, concave up and to my point of inflection, x is equal to 0. Notice I have a minimum at negative 3 and concave down all the way beyond that and a maximum at x is equal to 3. So you notice how all these little pieces came together and fit together to give me my graph. Notice, by the way, my derivative was a quadratic, so my original function was a cubic. I wonder if there's a connection there. All right, in summary, so we'll be able to use the derivative to explain many features of a graph, and the derivative and original function are connected in so many different ways that we can see graphically. I know this was a little bit of a long video, and I know there's a lot of information here, but we're going to talk about this in class, so give it your best shot. And as the whole year goes along, we will continue to discuss this. All right, thanks for listening. We'll see you in class.